Okay. Okay. Now we're gonna go here. Let me just make sure she's up and running. Yeah, she is. Oh, but she lost all of her stuff. Hmm. Oh, it's because she's not. Okay, yeah, I have to. Um. Oh, because that's the wrong CD home. And then I'm going to do. I'm gonna do the. Now I'll do the Docker command. Fix D. Yeah. To remove. Okay. Okay. Okay, so now that that is correctly created, let's just double check her help. Help. But she probably needs a couple minutes. Yeah, she just needs a few minutes to get started. Okay. Back to what we were originally doing. Did I finish? Why am I looking in my file explorer? I can just look in Vim. Yeah. Okay. Um, hmm. I wonder if there's a good. I don't really want to fish around for plugins. I guess I'll just download the .py. Yeah, that seems good. That seems good. Get that out of here. Let's download a .py. Yeah, it'll probably be faster if I do it this way. Well, what is this fucking thing called? Got it. We're gonna do .py. Missing destination, right? Can I do it here? You say, oh, cool. I did not know that. I wasn't sure if MV worked with just like a come here command. Okay. Why? Okay. Why did that .py file not? Okay, I guess I am gonna have to open my Explorer. The frick? Hello? It's .md. I want like .py though. Birds. Oh, because it moved it. Okay, well, let's double check the actual birds Python file. Um, oh, hmm. Okay, maybe I guess I will have to go find a Neovim plugin. Let's see, is there a good way for me to find that? I don't know if there is one in Lazy. Alright, uh, running code interactively with Jupyter. Um, does that mean I'll have to install all of those thingies? I guess I can just ask. Oh, brick. Page, please. Wow, that sounds terrible. Am I gonna have to? I'll check the lazy vim readme. No results for Jupyter, huh? Okay, well, since I'm not playing the video yet, I should probably switch it to something more interesting. So let's go here. How do we into NeoVim and Jupyter at the same time? Use my own fork. Oh my god. Iron.envim sounds useful. Let's double check. Nope. Okay. move quickly across cells. Okay, so this will give me, let's see. Excuse me. You can mix it, you substitute iron with magma, and you can edit Jupyter notebooks with the magma. Alright, let's take a look. Remote in with putty. Okay. So Jupyter notebook on the other was okay. Switch tabs in the browser as you search. Actually, I want this anyway, because I want to be able to harpoon web pages, and this sounds like I can do that. I could not figure out for the life of me how Prime was doing that, so. Or like said that he did that, but I assume it's just because I'm on Windows and he's on Linux. So I heard him mention it offhandedly one time. Keep a copy of that buffer. Okay, I don't really need to know how it works. It's fine. Um, oh, 3 days ago, do we have a release? Mm, 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 mm. Hmm. So I still want to use Notebook V6. And B Classic will be... Okay. This looks like what I want. This is the new default setting. Okay, if that's the default setting, that's fine. So I'm still going to have to deal with this. Okay, I don't... Do I need 3.7 specifically? Because I don't really want... Well, I guess that's kind of on me because Venv, right? I should modernize, I suppose, but... I wonder if I will remember what all to install. I kind of doubt that I will. So I'm leaning towards we actually leave Vim if we're going to do Jupyter stuff, which I guess is kind of the point of Jupyter stuff, but sounds cringy to me, bro. Now that I'm inside Vim, I never want to leave. I'm sure if you've been there, you know what I'm saying. Vim, by the way. Vim user, by the way. Let's see. Mm, cool.
So, hi everyone, hi again. I'm Akanksha and welcome to the week two of our CUDA mini cohort. So, last week we went through some fundamentals to help you get started. We learned about processes and threads and time slices and concurrency management and pitfalls. And in today's session, we will go through some of these concepts in detail and then look at how to avoid concurrency pitfalls as well. So, if you missed the last session, the recording is available. We have shared it and we encourage you to go through it. So, cool. Let's start with today's session. Next slide. So we learned that executing multiple tasks at the same time in your programs is basically known as concurrency, and it makes your programs faster, more responsive, and it is able to handle multiple operations simultaneously. Next slide. Let's quickly review what we learned about processes and threads. So basically a process in a computing environment is an instance of the computer program that is being executed, and it has these three basic components: an executable program, the associated data needed by the program, so like variables, workspace, buffers, and all that, and an execution context of the program, so the state of the process which is stored on the stack. Next slide.
Someone is sick.
And we
It's
also
so
learned
weird.
that a thread is an entity within a process that can be scheduled for execution. So it is the smallest unit of processing that can be performed by the OS. So it basically contains all this information that we are seeing on the screen in a thread control block. Let's understand the components of this block. So what is a thread identifier? So it is basically a unique ID which is assigned to every new thread. There is stack pointer that points to the thread stack in the process. The stack contains all the local variables under the thread's scope. The program counter is a register that stores the address of the instruction currently being executed by the thread. Thread state is it can be running, ready, waiting, starting, or done. And threads register set is basically the registers assigned to the thread for computations, and parent process pointer is basically pointing to the process control block, which is the similar stuff for the processes where the threads live, and each thread contains its own register set and local variables which are stored in the stack, and all threads of a process share global variables stored in heap and the program code. Next slide. So now moving on to multi-threading, we learned about it in the last week, but let's understand it in detail. So as you can see from the diagram also, like it involves multiple threads of execution running concurrently within a single process. So it's like we learned that it's like having several workers in the kitchen, each performing a different task at the same time, sharing the same space and tools. And Yeah, so this is particularly useful for tasks that spend a lot of time waiting for external events like network responses or user input. So In a simple single core CPU, it is multi-threading is achieved using frequent switching between threads, and this is called as context switching. And we also learned that the state of the thread is saved, and the state of another thread is loaded whenever any interrupt due to I/O or manual intervention takes place. So we also learned that context switching takes place so frequently that all the threads appear to be running parallelly. So this is multi-threading. Now let's look at this in detail in the Colab notebook, how we can achieve this multi-threading. Here, can you go to the Colab notebook?
I don't know why. Why is that an invalid tag name?
So yeah, we will learn about how we can see the multi-threading in action using this small piece of code. So as you can see, this first block of code, right? So it is we are importing the threading module, and then we are basically checking here that so let's say let me give you a background about what this function is exactly doing, the thread task. So it is taking two parameters. One is name and the other is delay. We are trying to start two different threads and introduce a delay between these processes just to see how multi-threading takes place. So here the time sleep delay is going to be the thread pause thing for the number. So basically it is the number of seconds that will be causing the thread to pause. So this simulates a task taking some time to complete. After the sleep period, it prints the thread that has finished, noting how long it took. So as you can see here, thread 1 and thread 2 are created using the thread class from the threading module. The target argument specifies here the function that the thread will execute. In this case, both threads will be running the thread task function, and the arguments 2 and 3 are basically the time
Target.
delays.
Okay.
So using thread 1
Starting the thread.
dot
Okay.
start and thread 2 dot start, we basically start these thread instances, and this start method internally calls the run method, which in turn calls the target function, which in this case is thread task with the arguments that we have provided. And once started, the threads run independently. So the order of their execution is not guaranteed, and it depends on the operating system's thread scheduler. But since we have a delay also here, we will see that when
Wait a
we
second. What was that?
it is. And once started, the threads run independently. So the order of their execution is not guaranteed, and it depends on the operating system's thread scheduler.
So the order is not guaranteed, and it depends on the operating system's thread scheduler. Okay. That. Hmm. Okay, but like, what if I need it to be in a certain order, right? Do I just have to like sleep and guess? It's kind of weird.
But since we have a delay also here, we will see that when we run this method function, we will see that the task so sorry so thread 1 where the task is to wait for 2 seconds, and thread 2 where the delay is of 3 seconds, we will see that if they had not ran if they are not started at the same time and run at the same time, we would have observed a delay of, let's say, 5 seconds before the thread B shows this statement that thread B finished after 3 seconds. But it doesn't happen. There is only a 1 second delay when we run it, which proves that basically these threads started at the same time and were running parallelly. So yeah, the join method also, let me
Ow.
tell you about that. It is basically used to make the main program wait for the threads to complete their execution. And without this join function, the main program could contribute to the next line and finish executing, possibly terminating the threads prematurely. So we don't want
Okay.
that. So by calling join, the main program blocks until the thread on which join is called is finished. So yeah. that is how we see multi-threading happening in action. Uh, can you go to the next block here? Yeah. So, for example, here I wanted to see if uh, I can demonstrate that sometimes there is a possibility that we cannot see that exactly these threads are being run simultaneously. So let's say if we just do a simple task of printing these numbers, right, 1 to 10, let's say, uh, you can increase these numbers to see if there is some interleaving in the outputs. But at 10, it so appears that thread A seems to run continuously at first, and then it starts the thread 2, which prints the value of B. But if you increase the value to 100 also, I observed that it was doing the same thing. So basically, it printed all the A values first and then B. So it seemed like, okay, maybe thread 1 is running first and thread 2 is running after that. So sometimes this happens because the OS has this thread scheduler that controls when each thread runs, and basically depending on the system and its current load, the scheduler might allow one thread to run to completion if the system is not under heavy use. And for simple tasks like printing output on the screen, it that can definitely happen. So that's why we go to next code block. So that's why we, let's say, allow some time delay here. So as you can see in this block that we have used time dot sleep function. So using this, we allow some interleaving to be observed in the output. So if you see the threads A and B seem to be printing one after the other. So yeah, that can probably show you more in detail about how they are working simultaneously. So it may not be necessary that you observe it in the output
What's up,
because
John?
sometimes it can be a simple task like printing.
Sorry, I don't
But
have my chat
yeah,
on the screen,
this
so I can't really
demonstrates
see.
that we can see
Actually,
it
in
in
theory, I
action.
do. Yeah, I do.
Can you go back to the PPT now? Okay, so that's what we saw in the multi-threading. We saw it in action, and let's now focus on multiprocessing.
I have Obsidian
Uh,
open and I'm
it
taking
is
notes in that too, but
this involves multiple
um,
processes, each
it's also
running
got my
in
personal
its
vault
own
in it,
memory
so I don't
space,
want to accidentally leak shit
and
everywhere.
this. I think you can think of it like having multiple kitchens, each of its own set of tools and workers, like we discussed last time.
Okay.
And this approach is basically ideal for CPU intensive tasks such as data crunching and complex calculations. We will also learn how and when to use multi-threading and multiprocessing. But before that, let's
Back that up. What's multiprocessing versus
like
multi-threading?
having multiple kitchens, each of its own multi-threading. We saw it in action, and let's now focus on multiprocessing. Uh,
Okay.
it is it this involves multiple processes, each running in its own memory space, and this I think you can think of it like having multiple kitchens, each of its own set of tools and workers, like we discussed last time. And this approach is basically ideal for CPU intensive tasks such as data crunching and complex calculations. We will also learn how and when to use multi-threading and multiprocessing. But before that, let's check how multiprocessing works in the notebook.
Okay.
So for multi-processing, do we have separate stacks and heaps, or do we have the same?
We have separate. So it's a completely different processor that is going to have its own stack and this like all of the different components, and you will have multiple threads running on them separately.
Okay.
Oh, that makes sense. Thanks.
Yeah. So yeah, if you go to the code block now, here each process is basically calculating the square of a number independently, and it prints out the result. So unlike threads, these processes do not share the same memory, ensuring that one's process operations do not interfere with another's. And this isolation basically requires more system resources, but provides a robust way to handle tasks that need to be truly independent. So as you can see in this, there are two different processes that are running, and we see the output on the screen. We can also, next code block.
Start the pro. Okay, it says, yeah, okay.
So yeah, this here you can see exactly what is the process ID and how they are differentiated also. So in the output, you see all these different things like ID of the main process, ID of the process running, worker one and worker two, and you can see that they have different IDs. So the main point of this script was that to show you that all these different processes are executing on separate processors. So the objects P1 and P2 in the above program use the OS dot get PID function to get ID of the process running at the current target for the current target function. And notice that it matches with the process IDs of P1 and P2, which we obtain using the PID attribute of process class. So you can also use it and play around with it and try to observe these things. So here each process runs independently and again has its own memory space. So yeah, yeah. Can you go back to the PPT now? So yeah, let's learn when can we use multi-threading and when multi-processing makes more sense. So the choice between them depends on the problem at hand. In case of parallelism is needed in.
Okay, one sec. I need to check and see if they dropped off the slides so I can import them. Rip. It appears as though they did not. Can I store? I guess I can just store the raw Python in Obsidian so I have it for reference later. That's basically whenever oh, actually, yeah, I can just transcribe this. Most of the time, actually, let me see if I can do that real quick. No. I like to, if I have the option, I like to put as much of a class as I can just directly into Obsidian, because I'm dumb and I forget stuff a lot. But if I record all of the material that is involved in the class, then if I remember something that's vaguely related to a problem I'm having, then I can effectively like externalize the smartness. I can just like I can go put it in the brain where I don't have to like worry about it falling out of the meat part.
Let's say the running entity are related to the terms of data, then multi-threading can be the first choice. So let us consider two interesting use cases. In the use case one, let us consider that we are designing a HTTP web process, and a designated master thread can handle all the HTTP connections here, and multiple worker threads can serve the HTTP request. And in this case, the HTTP request data is shared between master thread and worker thread. What is a master thread? It is basically the initial thread in an application, which is typically the main execution thread of the program. And worker threads are threads that master thread spawns to perform specific tasks or.
Okay, so for an HTTP web process, it's going to have a master thread that is the HTTP web process, and then it's going to have worker. We don't use the other term anymore. It's going to have worker threads, um, which are individual pieces of that HTTP web process. And what I imagine the reason behind that is because there's not a lot of complex calculations being done to just manage that HTTP web process, because it's not doing anything complicated. Like it's not doing math, or something you would really need like an individual processor for. That's my guess.
portions of the task. So yeah, that is our first use case. And the main execution thread of the program. And worker threads are threads that master thread spawns to perform specific tasks or portions of the task. So yeah, that is our first use case. And the use case two is that programmer needs to, let's say, collect information from various sources and then store these informations on the database. So here are the two components of this use case: the collectors, which fetch information from various sources, and database manager, which stores the data. So for collector, multiple processes make more multi-processors multi-processing makes more sense, since it allows horizontal scalability. And note that multiple collectors can separately run in different machines and communicate with the database to write the data. So we don't need to have them on the single processor. So uh, collectors can run periodically, and so there can be
Okay, that's interesting. So what I wrote down was that the multiprocessing is for horizontal scalability, kind of because we don't need them on the same machine. So it's like what my brain is doing there is like instead of thinking about instead of thinking machine first and like okay, I have an operating system and then what can I run on it? Um if you think kind of like the opposite direction where it's like okay, I have if you do task oriented thinking, I guess, then it's easier to decide like okay, is this something that is going to need its own processor? If so, how many total processors do I have available? Okay, then I'm going to need this many machines and I'm going to use multiprocessing. If it doesn't need to do complex calculations, although so this kind of makes me want to look into like Redis, because my understand Redis, however you pronounce it, because my understanding is that Redis is really good at doing horizontal scaling. In is if I have my definitions right, um, because you can just like huck a shitload of data at Redis and it'll handle it, as opposed to some other database. Maybe SQL, although I don't know. I guess it depends. Others that need the oh yeah, it's because it keeps everything in RAM. I think that's why. So it's good for um multi-processing. So CPU, and what it has is a lot of active memory. Hmm. Okay. Well, I'm interested. I wonder if Akanksha is going to clarify
again
a little bit. We'll see.
asynchronicity in the single-threaded implementation, which makes high-performance code run in different machines and communicate with the database to write the data. So we don't need to have them on the single processor. So collectors can run periodically, and so there can be an asynchronicity in the single-threaded implementation, which makes high-performance code simple to maintain. And for database management, a single process with multiple threads makes more sense, since it avoids inter-process lock to access the database.
So processor with multiple threads makes sense. So that there isn't a because locking threads. Okay, so if I'm multi-threading, I'm avoiding process lock if I do it right. But that's, its own sort of art form, I guess. Um, Okay, so multi-processing is each so the process wants its own processor, whereas it does can I on a given processor in a multi-processing architecture, can I multi-thread on a given processor? Presumably, yes.
And database manager needs to provide better response time, and so it needs to use multiple threads. So this is one example. Now I mentioned that it avoids
What?
and database manager needs to provide better response time, and so it needs to use multiple threads. So this is one example. Now I mentioned that it avoids interprocess log when you use multi-threading for database management. So let us see what exactly it is. Next slide. So, if you remember, we had discussed about the different concurrency pitfalls in the last week's session, and one of them was race conditions. We can avoid these using thread locks. So, what are these? So, thread locks are a synchronization mechanism that prevents multiple threads from entering a critical section of code at the same time.
Prevents multiple threads from entering section of code at the same time. Okay.
It's like having a single bathroom in the house. Even if there are many people, only one person can use it at a time, so that can be understood as a thread lock.
I mean,
So the thread locks basically prevent race conditions where threads might corrupt shared data, like in the database management, that use case that we just saw. Let's see it in collab. So yeah, this last code block that I have here, it is basically doing the same thing that we just spoke about. It
okay,
is
threading that
trying
lock.
to,
Sure.
so here without the lock, as you can see in the code, the counter value would be unpredictable because threads could interfere with each other's operations. And with the lock here, we ensure that only one thread increments the counter at a time,
Python is so
leading
stupid.
to a consistent
Finally.
and correct result, as we can see in the output.
Oh
So
god.
this example clearly basically shows that how locks can prevent data corruption. You can also play around with these code blocks and check different observations. So yeah, over to you, Aaron.
Thank you, Anka. Yeah, hi everyone. So I'll be talking about queues, semaphores, and mutex. So let me ask you one thing. Uh, when we talk about threading, in among yeah, sure. It's currently in edit mode. Let me push it in. Oh, it's in view mode. Perfect. So you can access the Collab notebook here. And yeah, so when we talk about threading, we if let's say if Python was able to access somehow do multi-threading, right? It all the threads.
Wait, is this Jupyter notebook not written in Python? And is there not, right here, an example of multi-threading? Or is this just like we're pretending to do multi-threading? Um, and yet, like, we're getting the desired outputs somehow. I guess we'll find out, but I'm gonna grab water real quick though.
would share the data and the resources that run on the process. So everything amongst those threads are shared. But when you're working with, say, like processes, which is much more relevant and probably more frequently used in Python to achieve true concurrency or parallelism, these things becomes a bit difficult. So you can't actually share data amongst the processes directly, right? So to solve that issue, what we have is some.
Hmm. Presumably, we use queues.
Something called as multiprocessing queues. So multiprocessing queues is a data structure which all the processes can access and modify without running into a deadlock or any probably or any sort of failure in terms of fetching and pushing. So how many of you know about queues? If you don't know about queues, let me know in the chat. If you know about queues, just write one, and if you don't, just write zero.
0.
Okay,
I
so
mean, like, I
okay, yeah,
understand the concept, but
I'll still talk about what queues are. So imagine a list, right? When you're talking about Python list, what you can do is you can add elements by append, right? And when you append an element, it gets added to the end, right? That's quite same as queues. When you add something to queue via the put method, you add an element at the end of the queue. It's kind of, just think of like a list in that sense, right? But this is where things change. With list, you can access each and every element of queue, right? But that's not sorry, each and every element of the list with indexes. But you can't do that with queues. With queues, you have a special method called as get. So with get, what you get is the first element at the queue. You pop it out. So you say you have a list or a queue, 1, 2, 3, 4 as elements. You say put five. So five would be added at end. The queue would be 1, 2, 3, 4, 5. But when you say get without anything, just get, it will give you one. And now the queue would be 2, 3, 4, 5. Such type of data set, this queue works on the principle of FIFO, first in, first out, right? And then there is stack, that is last in, first out. So whatever is added at the last would be popped out first. That's stack. But queues is first in, first out. So the first element you put, it would be out, right? So with this queue, you can do the same thing, but share it amongst all the processes. So
oh, I just thought of something. I need to do it before I forget it. You go back up here to go down to this, and then I need to do 9:30 a.m. So I need to I need to calendar. Oh, nice. Yeah, I have birds then. LOL. 9:30 to 10:30. Now the question is, governable spaces book club. Weekly on Friday. Man, tomorrow morning is packed, bro. The struggle of being a theoretically employed person and having filled up my calendar prior to my employment journey, I guess. Where was that? What are they doing? Notebook, right? Oh shoot, did I just leave my calendar everywhere? Oopsie. Oh well, it's fine. I guess you have context now.
each and every process could modify this queue, and other process would be able to see that change. Now this queue only takes max sizes argument, which is the size of queue, right? And in order to check if this is empty or full, you can use these two methods, empty and full, to see if it's empty or full, right? Now, if you try to put an element, if you try to put an element in a full queue, it would be blocked. And if you try to get an element from an empty queue, it will be blocked. But you can override that block. You say, okay, don't block anything, do it regardless of whatever. So you can use put element block equals to false, or put no wait method and add the element without any block. But if there is no possibility of adding or receiving, you'll get an error. So you'll need to handle that error, right? So let's dive into how we can actually use queues. And if you are aware of the midweek question that I put, it came from this. Yeah. So let's talk about this. We have a queue. We check whether it's empty. We check whether it's full. We put two elements into it, one and two, and then we check the status again, right? Now, ideally, initially the queue is empty. So this would be true. As you can see here, it's true. And the full statement would be false because queue is not false, it's empty. So it would be false. Now, when you put two elements to it, max size is 2. So the queue is full now. So this should be false because queue has some elements, right? And this should be true, as you can see here. But funny thing is,
I'm having thought maybe after this, yeah, are you gonna, George, are you gonna make me, he's gonna make me click through his fucking GitHub repo. George banned me from his Discord because I said the word blockchain. I will never forgive him. I was trying to explain where I got all this free compute from that I was trying to give away to people. But such as it is. It was a good meme though. I was like, is this a place where I won't get banned immediately for saying the word blockchain? And then apparently somebody reported to me later that he banned me and then said banned for using the word blockchain. So the sacrifices must be made for the proper memes. So so scheduler. Okay, so this might be helpful. What I'm hoping is maybe by the end of Bird's CUDA edition, I might be smart enough to start thinking about tinygrad. Currently, I believe I am too dumb. But we'll see.
this is actually true, which is weird, right? So what happens is we can just put a sleep. It's just a matter of how quickly stuff gets executed. You can add a sleep over here or a delay of 1 or 0.1 or something. So when it executes, it has the correct or expected queue in our mind, right? Just to synchronize the state. So sometimes print outputs can behave unpredictably, right? There could be asynchronous display, output buffering, and whatnot that could result into this. Now, if you need to see the size of the queue, you can use a method called as queue size, and it will tell you how many elements are in that queue. Same as put, where you push an element into a
This is a
queue,
fucking troll.
you can use get.
You're really gonna switch from Q to Q, you little shit? Fine.
and with get you'll get the first element that was added. So first we added 1. So when we
This is
add
why I
when we
generate all
use
my
get the
fucking
first time,
code.
it will give us
I'm not
1.
gonna remember
The
that
second
shit.
time it will give us 2 because it was added in that order. The order in which you insert is the order in which you get, right? And now the queue size is 0. So let's take a working example, and I'm shamelessly copying it from the blogs that I provided in the resources. So we have a function over here that checks whether any number is even or odd. It's pretty simple, right? We take it takes a value x, argument x, and if it's divisible by 0, it's even, else it's odd. I really don't think there is any HP, so it's fine.
Hmm.
Now we have two function over here. This is called a producer function, which produces n number of random numbers, and consumer and pushes it into the queue over here. Then we print bunch of stuff. Whereas with consumer, we basically get the values from queue. If the number is none, the value we received from queue is none, it will break from this loop and check. If not, it will continue
Okay,
and
I see.
check the result and then print bunch of stuff. Now, when you execute it, let's see what we are doing here, right? We have two producers running concurrently. We have four consumers running concurrently, and we
Oh,
have
okay, that gets
10
more
numbers that
interesting
would be
in
created.
this context.
So, in this process, in this part, we are creating a list of processes that would be triggered when we run start, right? So these processes will take producer.
Really quick. So I know that I am going to want to, I know that I'm going to want to transcribe this afterwards. And I guess I could just do it with Obsidian, but I want this up anyway. So I'm going to grab a little handy dandy little thing. I want, shush. Yeah. I'm gonna double check and make sure this works. Pretty sure. Onto modal, right. And then I made an issue on it. And I just wanna, did I deploy modal app or shush.py? Okay. I'm gonna clone this puppy real quick, just so I got it. Because it's a nice thing to have around. I go, we're gonna go cd active. Do I not? Oh, I'm still in repos. cd active ls git clone paste. Okay. Okay, we'll exit from there. I just wanted to do it while I remembered it.
And the arguments q and n numbers, as we studied in the multiprocessing portion where we learned how we can define processes, right? And once and for consumers, the target would be consumer, and we'll create n consumer instances for this. We'll run the producers and consumers, and then we'll join all the producer instances. Now, once all the producing is done, we'll put none into it. How many none? N consumer nuns, because we want to finish all of those. And once that is done, we'll start. Finish. We'll wait for the consumer processes
Why
to
is it 10
finish.
o'clock already, bro?
So first we'll wait for processes to finish and producers to finish, and then we'll wait for consumers to finish. So once that is done, our program finishes. So we start main, and it's doing what it's doing. It's just printing weirdly because of the stuff I talked about. So how can we prevent that? We can add a delay over qput and qget, and that would be fixed, right? But you must be asking here, why do I even care about this, right? It seems like something useful, but does anyone even use this? And the question is, yes, I'll take you through this code base, and this is a technique called as it's an implementation of a paper called UDABDER. It doesn't matter what this paper is about, but what matters is how it uses queues over here. So queues.
Okay. I assume this is a repo that I'm gonna include it in my notes. So we're gonna go to Prime QA. And then where are we at? Extensions. We are probably gonna want to end up ingesting that paper, but for now, just gonna take a little screenshot there. I don't know if I'm gonna have like, I don't know if I have time to do this
So
homework.
here we are defining a queue, and it's the same thing. Like we are using torch for this to create the queue, but it's the same thing. So we use this queue and pass it in this as an argument in this process. And what this is basically doing is that it's creating a bunch of data across multiple processes. So it's going to trigger multiple processes which are going to create some sort of data, and that's going to be appended to the queue. And once that is appended to the queue, we are going to dump all the data in the queue into another list. So create multiple processes, create multiple data across those processes, push it all into the queue, and then finally gather all the data that was present in the queue. So this is how some real life code bases actually use queues. Could it have been done without queue? Yes, probably. But yeah, there are multiple ways to do multiple things, and yeah, I think this was the most optimal. So yeah, that was about queues. Now we'll talk about mutex. And we just talked about thread locks, right? In Python, mutex actually doesn't exist as a term or a module, right? So why am I talking about mutex? So just to be clear, mutex is from a family of objects or modules or algorithms called synchronization primitive or concurrency primitives. And these basically prevent multiple threads or processes to access a critical section of a code. And that critical section could be anything that could lead to a potential corruption of data sharing or data management, right? And this is important. Now, in Python, mutex is a lock. Lock is basic. In general terms, lock is much more of a broad term, and mutex is a very specific kind of lock, right? But in Python, both of them are same. But in languages like C and Rust, mutex is what we use, not locks. So it's very much dependent on the context of what we're talking about, of what mutexes are. But the principle is execution, mutual exclusion.
Okay, I need to check something. Mojo language, mutex. Mutex abstraction, okay. I am, mutex. I've had Mojo on the mind lately because they have that new release extensions and such. So just wanted to see how Mojo handles that, and as such, if Mojo cares when Python does not care.
Of accessing same resource, right? So think about this. You have two processes running, and process one accesses some resource. It applies a mutex lock on it. So when process two, who's running at the same time, tries to access this element, its access is blocked. Once process is done with this resource, it releases the resource, and mutex lock is released. Now, when process 2 tries to execute the same thing, it is able to access the resource and apply the mutex lock on it. Now, process 1 tries to gain hold of it, but is blocked because process 2 is having a lock on it. And once process 2 is done, it will release the lock. But you must be asking, okay, in Python, they both are the same. So why we are talking about this? So someone once told me that mutex is one of the most important concepts in distributed systems. So it's good to discuss about this, and especially when talking about Rust and C, it's more common to use the word mutex than lock. So there are these two papers that you can read to learn more about mutual exclusion. And the first time mutual exclusion was coined was by Dijkstra. If you are familiar with graph algorithms, you might know Dijkstra's algorithm. So he was the same guy, and it was coined by Dijkstra in this single paper. It's just a one page paper, and it talks about the problem and the proof. And this paper dives a bit more into it, right? And yeah, you can go and read these papers, and yeah, that would be good. Now we'll talk about another type of synchronization or concurrency primitive called as semaphore. Now with locks and mutex that we just talked about, they make the resource or whatever critical code section very exclusive. Like it could only be accessed by one process or one thread. But many times what happens is you might need multiple processes to share a resource, but to a certain limit. You might think that this resource could be shared safely up to for two processes or three processes, or probably limit how many people how many processes can have a lock on it. And that is exactly what semaphores do. So semaphore maintains a counter of how many mutex locks are done, and based on that executes or assigns the lock to the processes. So let's say there are 5 processes being executed in parallel, and and there is a resource that could only be shared by two processes at max. So process one accesses it, applies
Sorry, something just failed. Okay, I don't care. Doesn't matter.
applies lock on it. Now our semaphore has a counter of 1. Next process 2 does it. Now semaphore has a counter of 2. Now third tries to do it but is blocked because there could only be 2 semaphores or 2 shared locks across the processes. So that's what semaphores do. It's more lenient mutex, I'll say. It's not exactly mutual exclusion, but yeah, it's a type of mutual exclusion. Now, I have a question for you. How many of you understood? If you are not able to understand something, do let me know right now. And if you are able to understand semaphores and mutations and locks and whatever, can you tell me a condition in which semaphore would become a lock? This is the question that we'll also have an assignment. So yeah.
Oh Lord. Okay. Fuck. Puts a limit on the number of processes or threads, so I guess I will go ahead and share this just so I have. Okay, so you can see my notes here, maybe? Yeah. Okay. So, when would a semaphore become a mutex lock? A synchronization primitive that's used to prevent multiple threads from accessing a shared resource of critical section of code. This is essential in multi-threaded applications. Python, same as a lock. Mutex. Okay. Acquired resource, accessing resource block. And then released, accessing resource. Okay, and then a semaphore is a limit to the number of mutex locks. Another type of concurrency primitive puts a limit on the number of processors that can acquire a lock. So when does a semaphore become a lock? Well, presumably when the limit has been exceeded, right? Because if a process is trying to acquire a lock, but it can't, then that process is effectively itself locked, I think.
Is there a condition where you can think that semaphore acts exactly like lock or a mutex?
Semaphore 1.
Yep, exactly. So if you have a semaphore with counter 1 or limit 1, it's going to act exactly like a lock, right? Only one process can be having an access to that, and
Okay. Sure.
that's basically it. And now you might be thinking, so
Wait a second. Only one process can have access to that resource. Can have access to that resource. And when I am accessing a resource, I am attempting to lock the target. Right? Because I need to use it. Okay, that makes sense.
so binary semaphores are kind of like mutex, right? In some cases, if you have gone through the resource that I sent, in there over there it's also written that binary semaphores are also like mutex, and in some cases they are not even differentiated, but there is a difference between both of them. So yeah, that's a bit of theory about semaphores. Now here is this code block of how we can use semaphores in Python. There is a semaphore object in all three types of concurrency or coroutine libraries. Like multiprocessing has its own semaphore module, threading has its own semaphore module, async has its own semaphore module, and all of them are kind of different, but yeah, they essentially refer to the same concept. In order to use a semaphore, it's pretty much the same as a lock. You have a task, you acquire a semaphore, and then you release it when the process is done. But you can avoid that acquire and release writing again and again by just using it as a context manager. So you say with semaphore, where semaphore is passed as an argument and does some stuff. In process, we
Oh, a context manager. Maybe that's okay. Sometimes I don't know. I learned stuff. I like originally learned stuff in JS, and it was like web3.js. So, sometimes when I see stuff in Python, it like looks really weird to me. So, a context manager is semaphore. I might grab a wiki article and shove it in here too.
pass semaphore as an argument after declaring it as an object over here and start and gather all the processes over here. Same thing is done by this, just that instead of using a context manager, we are writing acquire and release explicitly over here, and it does the same thing. Now, before ending this session, I have two things to talk about. First, is multi-threading always good? And this is not something that we'll discuss, rather something that you should think about, because this is also going to be in the assignment. Is multi-threading always good, or is multiprocessing always good? Like one example I can give, like in many cases, probably threading looks like a good option, right? For most things, threading looks like a faster, better option, right? But think about this. When you see Task Manager, Google Chrome has processes running instead of threads, right? So is it always a good idea to have multi-threading as an option rather than or are multi-process always going to be communication expensive, right? That's the first question I'll ask. Second question is multi-threading so, like, is single thread so bad? Like, is multi-threading always going to be faster and single thread always going to be slower? Now I'm going to stop the recording because probably the next section or whatever I am going to talk about should not be recorded because of, I don't know, I paid, the information I'm going to give is from a paid cohort. I don't think I can share it in the recording.
Well, frick.
Yep. So I did.
Dang it, Hiram. Give me the free stuff. That's so stupid to me. Like, oh yeah, I paid for this course, so now I can't share it with anybody. Like, what the fuck? I don't know. Humans are weird. Okay. So we have an assignment, and then we have a Well, we have a thingy. Okay, so let's start with this. Well, collab is not done, but good point. I should make a copy. What does the join method do in a threading context? Once it's completed, well, you might use a thread in a program that downloads web pages. If I want to download many pages at the same time. Okay, is this actually on screen here? Let me make sure. Oh, my Obsidian is blocking it. Let's take that and put it up here. And I guess I can hide this one too. Whoop. Whoop. And then we can put Obsidian back, I guess. Um, okay. Sure. What is the main purpose of a lock in multi-threaded programming? Multi-threaded. Purpose of a lock. I believe it's race conditions, right? What is a key advantage of using multiple processes instead of multiple threads? Processes share the same memory space. I believe it's that, if I'm not mistaken. Write some pointers on cooperative scheduling versus preemptive scheduling. Did we go over that? Don't make me ask Jippity, bro, because I will. I have no shame about Jippitying my homework. Pointers on cooperative versus preemptive. Give one example. Okay, so presumably. Okay. I'm not sure what they mean by cooperative versus preemptive, but I'm just gonna copy paste the thing. And then I'm gonna I am going to have, double check here, okay. GPT-4, people are saying that Claude is like the holy grail. I have been extremely disappointed so far. Actually, let me switch. I want a particular Jippity. I want my Socratic questioning. Yeah, this guy. Okay, I mean, you're telling me the answer. Previously he didn't. What he would do is, but I probably have to tell him not to do that. Okay. Okay, I didn't read that. Can you ask a series of questions that will help me arrive at the conclusions are provided. Here, answer. I want to make sure I learn it. Okay. Yes. Scheduling. How do tester threads run on a processor? To have control of the CPU and how it might switch from one task to the other. So that's what the threads and locks are. If a task running on a CPU does not stop or yield on its own. Then it will overuse it, right? Where tests voluntarily give up control. Oh, if they're lower priority. Yeah, if you have a high priority task and it's asking, and a low priority task is currently blocking. A task not being forced by the system to yield control. Yeah, then your important stuff won't get run. Forcibly take control. Okay, so it's just priority. Never mind. Okay. Cooperative works best when I have a low priority process locking a resource. It should give up its spot for anything higher priority. The inverse should use preemptive. High priority processes or processes that need not be interrupted should preempt processes which don't have those qualities. Multi-threading always faster and single-thread execution always slower. Potentially no, but why? So he asked that question at the end and then cut his frickin' video off. Thanks, Hiram. But I would say potentially no, because multi-threading will have to account for lock targets, scheduling, priority, etc. Whereas if I have a simple process and I know exactly when it needs to, simple task, get completed and is a blocker task, i.e. it must be done before X other processes can start, then single threading, make sure it runs uninterrupted to completion could be advantageous. Okay. Or if I only have a very limited number processors, ideally I should structure things around being suited for single-threaded execution, since I don't have many to work with. I don't know if that's correct. That might be wrong, but whatever. Okay, better. Oh, I can't submit this yet, so I will need to go do this. Where we at? 10:30? Okay. Python program where two threads print alternating messages like ping and pong. Okay, import threading, ports time, def, thread print thread name I times sleep. Ping. Sleep. One. Actually, Pong is going to want to go after, so I actually don't want time here. I want ping to print. Ping. Fucking, I generate way too much of my code. I don't know if I'm supposed to do like return immediately or not. Return. Oh no, I'm not returning because I think I'm starting, aren't I? Thread one, threading. Okay. Time dot sleep one. Where's thread name prints? Okay, well that looks a lot nicer, but I think mine gets the job done. Probably should be reading the assist there. Do I need to include args? I guess I'll find out. I'll just run it and roll error out. Okay, I guess let's run it, see what happens. Okay. I mean, can I, fucking, give me that, let me get that AI, baby. Where you at? Oh my god. Thank you. I don't want to write that shit, bro. Cool. Thank you. Semaphore is used to limit access. You can just copy paste from the collab we used in the session. Alright, give it to me, baby. Make sure I understand it. I don't understand anything, bro. Okay, threading time and random. Threading does semaphore 3. Access the shared resource. Taking thread name as an arg. Acquire. Try. Simulate the accessing. So wait for a little bit. And then I accessed it. And then release it. 5 threads. Target. Threading.thread. Args. F-string. Thread I for I in range 5. Okay. So that is just an array that creates 5 of the threads. For thread in threads, thread start. So iterate through the array, start them all. For a thread in threads, join them all. So semaphore should prevent should lock. Okay. Want to just kind of give me a little bit of a better copy selection. AI. Bruh, what? Hello? Why did it only copy that much? Copy selection. Finally. Hello? Okay. What cell number is this? Alright, let me look at the next few. Oh, okay, so it's spaced it out. Got it. That's kind of what that's what I was looking for. I wanted to have like some sort of indicator when the semaphore was kicking in. Optional write a simple use case of mutex in C++. No need to run, just dump the code into a multi-line comment below. Sorry, bro. I care how to write CPP. Unless it's asking GPT to mod whisper. Okay. Well, that is what I do, so. Go away, fucking thing. No need to run it? Oh, I can't run it. Probably because I'm in a Jupyter notebook environment. Okay, let's go here. Okay, I just want to see this. So there are 5 processes. There are 2 tasks. Variables, there's a single fork between each pair. Okay. Must pick up the forks. Okay. Copy selection. Number of philosophers is 5. Forks is threading.log for blank in range. God, I hope I am able to. Oh, okay, so I can't copy it to my drive. Okay. Mm, 嗯 1, 2, 3, 4, 5, 6. I mean, I should probably um, so I can't iterate with the thing. That's fine. Okay. Well, that's homework for the evening. Yes, I did it all with AI. No, I don't care. Judge me. Because I'm gonna slap this whole ass notebook and the transcription of this video and basically all of the material I can find into this fucking obsidian thing, and then I can just recall it whenever I feel like. So, TLDR, you're stuck in using your meat while I have advanced beyond into the superior realm of Chrome. Not the browser though. Okay, we'll call it there. GG, well played. I am now caught up to week 2, and we're on week 4, so hopefully I'll have time to get